So, okay, we are here to study the interrupts of 8086 microprocessor. So, till here we have covered the addressing modes in the last class. We'll start with interrupts. Interrupts are of two types, hardware and software. And further, hardware interrupts can be classified as maskable or non-maskable. These hardware interrupts can be caused by the peripheral devices like keyboard, mouse, okay, by sending a signal through a specified pin in the microprocessor. The 8086 has two hardware interrupt pins. Okay, let's write it. NMI and INTR. NMI is a non-maskable interrupt and NTR is a maskable interrupt. So maskable and non-maskable. NMI, non-maskable INTR. So NMI, INTR. So in short, it's INL. One more interrupt pin associated is INTA called interrupt acknowledge. So it basically does not take the input of the interrupt. It confirms that okay, I'll acknowledge your interrupt. The microprocessor will acknowledge to the device. Okay, okay, hold on. I'm accepting your request. So this is that. So special INTA. Okay, next NMI. Let's study about NMI only. NMI. When this interrupt is activated, these actions are there. Completes the current instruction as fast as possible, pushes the flag register value on the stack, pushes the code segment value and IP instruction pointer value of the return address on the stack. The return address is when it will finish the interrupt problem, it will come back to somewhere, and the somewhere the coming back address is called return address. So it will come back to this address in the stack. So stack will have the flag register value, the code segment value, the instruction pointer value. And this instruction pointer will point at the address. Which address? Where it has to come back. IP is loaded from the contents of the word location 0008H. IP is loaded. IP instruction pointer is loaded from the contents of the word location. CS is loaded from the contents of the next word location. Interrupt flag and trap flag are reset to 0. So let's write it down. Completes the instruction whichever it is doing. Pushes flag register value. Pushes what was that? Code segment value. Pushes IP value. Instruction pointer. And this will point at return address. Loaded from the contents of the word location. Let's see what this line means. So I'll just copy it into the Gemini. Is 0008H an example, or it's always like this? It's always location for the initial instructor pointer, okay, of after the reset. So this is the default thing. So we have to remember. So IP is loaded from the contents of the word. IP 0008H and CS would be 0008H. Interrupt flag and trap flag are 0. So I flag, interrupt flag, and trap flag set to 0. Next. More about INTR now. INTR. INTR When this signal is there, same thing. It completes the current instruction. Completes instruction. Activates INTA input. Okay, in this type of the INTA activated only in INTA. INTA activated and receive the interrupt type say X. Okay. Flag register value, CS value of the return address, IP value of the return address are pushed. Same thing. Pushes CS and IP. IP value is loaded from the content of word location is loaded from the context of the next word location. Interrupt flag and trap flag is 0. Interrupt flag and trap flag is 0. 0. Yeah. Similar. Next, software interrupts. Let's study about the software interrupts now. Software interrupts. Software interrupt instruction with type number. It is a 2 bytes construction. Okay. What is this? Flag with register value pushed back on the stack. CS values pushed back. IP is loaded from the next type number. Info. Same thing. Type 0. Let's study about the types. Type 1, type 2. There are 5. So type 3 and type 4. Interrupt represents division by 0 situation. Division by 0. The type 1 represents single step execution. Single step execution. Type 2 is interrupt non-maskable NMI interrupt. NMI interrupt. Breakpoint interrupt. Breakpoint interrupt. Overflow interrupt. Overflow interrupt. The interrupts from type 5 to type 31 are reserved for other advanced processors. Okay, we'll skip that. INT3 breakpoint interrupt instruction. Flag register value pushed on the stack. CS and IP pushed on the stack. IP is loaded from the contents of the word location 3 into 4 CH. So here IP is 0000 CH. CS is the next word location. Interrupt and trap are set to 0. Into 0. Interrupt on overflow instruction. So overflow was type 4. So there is a typing mistake. Get pushed, flag register gets pushed on the stack. CS and IP gets pushed. IP is loaded 00 IP 00010H. CS and these two flags are 0. Pin diagram of 8086. And last page. Okay, this is the last page. So as you remember, pin diagram of 8085. We used to have VCC here. Now the VCC is here. The ground is used to be no VCC was here only. Ground was here. We used to have X1, X2. So now the ground and VCC is here. The buses are on the one side from 0 to 14. All NMI, INDR, clock and ground. Two grounds. Reset ready test. INTA, ALE. These things. HLDA hold. And these things. Okay, you can take a screenshot and study about this pin diagram. So this is also done. This is done. We'll study this interfacing devices and some programming. So this is the unit 4. Let's study unit 4. Okay. Unit 4 is more about 8086 architecture and all. So this is the timing diagram. Remember we studied the timing diagram of 8085. So it's like this only. There is one bus cycle is from the trailing edge of this to this. So you can say 1, 2, 3, and 4 time periods similar to that one. 0, 15, 16 to 19. Okay, 0 to 15 and 16 to 19 here. Address address out, and the data in uh, the ALE gets the pulse, input output, read when it's 0, and all these things. Trailing edge of ALE latches the address. Yes, trailing edge latches the this address. So it will become, it flips here. So it will become out. Memory write bus. This was memory read bus. This is memory write bus. Instruction set. What else do we have? Okay, we have to study this only, no? Let's see the difference between memory read bus diagram and memory write bus diagram. The AD buses are there and the address bus is there. It goes data in, status out. Okay, the BH is here, ALE, read, DDR, DEN. And in the memory write bus, it becomes, see, data in becomes data out, status out is there, everything else is same, I think. No, the data read, this changes. In the read bus, it is mostly at the 0. Now it is mostly at the 1. Read is same, DN is same, input, output, and memory same, ALU is same, BHE is same, address out, this address bus is also same, just AD was changed, changed, data in to data out, data in to data out, and all these, mm, you know, you can take all these arrows into consideration that at this point, this will point here, this will point here, all these things. Okay, instruction set opcode plus operand. Yeah, we know it. Opcode plus operand. Length 1 byte to 6 bytes. Output operation to be performed. MOD mode of addressing. REG register operand. RM register memory. D bit direction bit. 0 direction register operand is source operand. Register operand is destination operand. W data bit. 0 indicates 8 bit and 1 indicates 16 bit. S bit is sign. So 00 8 bit, 01 16 with 16 bit operand, and 11 means 16 bit operation with 16 bit signed extended immediate operand. Bhai sab, oh, we'll just remember that S is used with W, and W was 8 bit or 16 bit operand. Okay, so you can say 8 bit, 16 bit, 16 bit, and this becomes 001. So signed. So 8-bit operation with 8-bit W, 8-bit operation with 16-bit. It's something written wrong here. Here 16 operation with 16 bit. We bit used in case of shift and rotation instruction. Shift count 1. Shift count is register. G bit is used by repeat instruction to control the loop. Instructions. 1 byte instruction. Implied addressing mode. I'll say opcode register. What are these? DO to D7. Okay. DO3 are for the register and these 5 are for opcode. So total 8. Implied addressing mode. 0 to 7. All will be, or the 8 bit will be used for opcode only. Register addressing mode. Register is there, so 5 and 3. Okay. 2 byte instruction. So 2 byte means a 16 bit. So 1 byte will be move ALCL. So move, and then C. The first byte will be like this from D0 to D7, 8 bytes, D and W. D is direction bit 0 or 1. Whether it is from register to RM, register to register to memory location or register to memory location to register. And W is, it is either 8 bit or 16 bit. And then the other byte will consist of mode, these two modes, whether it is implied or register, and then register, then RM. Register to from memory without displacement. 1 byte, 2 byte mode, REG, RM, same, no change. But these changed, I think. No, no, no change. 3 byte instruction, guys, 3 byte. Now the opcode consists of the whole 1 byte. The mode REG, RM is there, and the third byte is 8-bit displacement or lower byte displacement, lower byte displacement. Because these are the same thing, na? 8-bit is low as compared to 16, and 8-bit is 1 byte, so lower byte displacement. Immediate operand 8-bit data to register. So you can remember this. There's move 43H plus SI. Okay, this 43H plus SI mode and DH. Immediate operand 8-bit data to register. So 8-bit data. So 8-bit data to register. So this is the register opcode, lower data byte, higher data byte to the register. This is the register 1, 2, 3. So 1, 2 will consist, 3, 4 will be here, and 1, 2 will be here. 4 byte instructions. Oh, same. Lower displacement, higher displacement. Here we have only lower displacement. And segment. 5 byte instruction. Opcode, same, lower, higher, and then lower data byte. In the segment, it was lower data byte, higher data byte, and here we have lower data byte. I think there will be a 6 byte. Yes, there is. Lower displacement, higher displacement, lower data byte, higher data byte. Assignment of codes with different register. Okay, this is there. Register code 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. No. 8. Then again 0, 1, 2, 3, 4, 5, 6, and 8. And this will become okay. A, C, D, B. It changed. Okay, okay. AX, CX, DX, BX. Next is this one. How can a student remember this? The last page is empty. 0, 1, 2, 3, 4, 5, 6, 7, 8. Mode 0, 0. SIDI, SIDI, XBP, SIDI. This is instead. We'll move on to Unit 4, guys. I think that was Unit 4. We'll move on to Unit 5, guys. And then at the last, we'll do the programming. I have my exam in the next few hours. So I'll try to wrap this up. How many pages is this? 55? Okay, we'll do a speed run. My exam is in few. It is within an hour. So serial and parallel IO chips. I will just write it. So as the sum of data, serial and parallel, serial and parallel IO chips. 8251, 8251, 8255. Programmable DMA controller is 8257. Programmable interrupt, programmable INT-C is 8259, 155, 5759. Keyboard controller 8279. Data acquisition using these things. Okay, next. Requirement of programmable interfacing device. The device should include input output registers, a group of latches to hold, tri-state buffers, capacity of bidirectional flow, yes. Handshake and interrupt signals, control logic, selectors logic, interrupt logic. These are the requirements. If the exam in the exam the question is this: what are the requirements if you have to choose a programmable interfacing device? It should have the input output register. It should be able to uh, have the bidirectional flow, data flow. It should be able to have the handshake and interrupt signals, control logic, interrupt control logic, and tri-state buffer. Hardware control serial IO using programmable chips. Functions and requirements SW, programmable, that is specifications. 8251, a programmable communication interface. This is the data bus buffer, transmit buffer, read write control logic, transmit control logic, modern control, receive buffer, receive. I don't think it was easy to remember this in one go. So let's just go to 8251A. But this is more chances of coming in the exam. The data bus 0 to 7, T ready, execute, control, reset clock, this. 85 data bus used to. We can see the function. So 8251 is used to read and write status command or data. Okay, from or to or from the same device. The control logic interface chip. The chip with MPU determines the function of chip according to the control word register. Monitor transmit signal converts a parallel word received from the MPU into serial bits. Receiver section receives serial bits into peripheral, converts them into peripheral words. No, I don't think we can cope this up. Buffer registers, expanded block diagram of control register. That was not enough. You have to expand it. Three buffer register in control logic. Controller register, status register, data buffer. Like if I had half or 1 hour more, I can do this. Then we have 8255, 8255, 8257, 8279, 8259. What I'll do is I will go to Gemini and please give a table having necessary info about 8251, 8255, 8257, 8259, 8279. कैसा गया? क्वेश्चन बताओ फिर। ये समझा दो मुझे जरा, जरा